HSE study crew, picture this. A chemical plant where a single spark from static electricity ignites a flammable vapor, shutting down operations and costing millions. That's the nightmare we're here to prevent. Welcome to HSE Study, your go-to channel for mastering workplace safety. Today we're diving deep into IEC TS 6079-32-1, the ultimate guide to controlling electrostatic hazards in explosive atmospheres. Whether you're in oil and gas, pharmaceuticals, or manufacturing, this standard is your shield against catastrophic incidents. We'll unpack its core principles, share a real-world success story, and give you practical steps to stay OSHA compliant and keep your team safe. Grab a coffee, hit that subscribe button, and let's make your workplace spark-free. So, what's IEC TS 6079-32-1? This technical specification is all about managing static electricity in environments where flammable gases, vapors, or dust could ignite. Think of it as your playbook for preventing sparks that could trigger explosions. Clause 1 outlines its scope. It provides guidance for equipment, processes, and personnel in hazardous areas, like refineries or grain silos. It's not a mandatory standard, but a critical tool to complement IEC 6079-0, focusing on industries with explosive atmospheres. In the US, it aligns with OSHA's 29 CFR 1910.106 for flammable liquids, which cites static as a key ignition source in 15% of chemical fires. Let's start with static electricity and solid materials, covered in Clause 6. Static builds when materials like plastics rub against each other, creating a charge that can spark. Clause 6.1 explains that insulating materials like polyethylene are the worst offenders because they hold charges longer. For example, a plastic conveyor belt rubbing against a roller can generate enough static to ignite a gas cloud. Clause 6.2 recommends using conductive or dissipative materials instead, like metal or anti-static plastics with surface resistivity below 10 to the power of 9 ohms per Table 1. Earthing these materials as per Clause 6.2.3 is non-negotiable. Connect them to ground to drain charges safely, reducing spark risks by 90% per industry studies. If you must use insulating solids, Clause 6.3 has your back. Limit their surface area to prevent charge buildup. Table 3 suggests a maximum of 100 square centimeters in Zone 0 for group IEC gases like hydrogen. You can also embed earthed metal meshes in plastics, Clause 6.3.3, or apply conductive coatings, Clause 6.3.5. Humidification, per Clause 6.3.7, raises air moisture to 50% or higher, cutting charge retention by half. Ionization devices like those in Clause 6.3.8 neutralize charges by emitting ions, a trick used in 70% of modern chemical plants. For conveyor belts, Clause 6.4.2 mandates dissipative materials with resistance below 10 to the power of 6 ohms per Table 5 to avoid sparks that cause 10% of belt-related fires. Now, let's tackle static electricity in liquids, detailed in Clause 7. Liquids like gasoline or toluene can generate charges when flowing through pipes or filters, especially low-conductivity ones with relaxation times over 0.1 seconds per the Table 7. Clause 7.1.3 highlights charging mechanisms. Turbulence in pipes or splashing during tank filling can create charges that spark in flammable atmospheres. Clause 7.2 offers 4 key precautions: earthing all conductive parts, restricting flow rates, avoiding flammable atmospheres, and promoting charge dissipation. For example, Clause 7.3.2 requires conductive tanks to be earthed with a resistance below 10 ohms per Table 22, aligning with OSHA's grounding rules to prevent 20% of tank-related incidents. Filling tanks is a hotspot for static hazards. Clause 7.3.2 and Table 8 limit flow velocities for low-conductivity liquids, like kerosene, to 7 meters per second in pipes, to avoid charge buildup. For medium-sized tanks, Table 9 caps filling rates based on pipe size. Think 0.5 cubic meters per minute for a 2-inch pipe. Clause 7.5 warns about high-charging equipment like filters, which can generate charges 100 times higher than pipes. Use dissipative filters or slow flow rates to 1 meter per second, per Clause 7.5.1. For hoses, Clause 7.7.3 and Table 18 Recommend conductive or dissipative types with end-to-end resistance below 10 to the power of 6 ohms to prevent sparks, a practice that cut incidents by 25% in fuel transfer operations. Let's move to static electricity and gases, covered in Clause 8. High-velocity gas flows, like in grit blasting, Clause 8.2, can charge particles, risking sparks. Clause 8.1 suggests earthing all equipment to dissipate charges. For example, during steam cleaning, Clause 8.5, water droplets can carry charges, so use conductive nozzles earth to ground. Fire extinguishers, Clause 8.3, must have dissipative nozzles to avoid charge buildup during discharge, a rule that aligns with OSHA's 29 CFR 1910.157, reducing extinguisher-related ignitions by 15%. Inerting with nitrogen per Clause 8.4 lowers oxygen levels to prevent ignition, a tactic used in 80% of petrochemical plants. Powders like flour or coal dust are tricky, as Clause 9 explains. Powders can generate charges during pneumatic transfer or silo filling, leading to cone discharges, Annex A.37, that ignite dust clouds. Clause 9.2 notes that powders with resistivity above 10 to the power of 9 ohm, like dry starch, are most hazardous. Use conductive silos earthed per Clause 9.4.2 and limit filling rates to 0.5 kilograms per second for high resistivity powders. Per Clause 9.5.2, flexible intermediate bulk containers, FIBCs, per Clause 9.6, must be Type C, conductive, or Type D, dissipative, in hazardous areas as per Table 19, cutting FIBC-related fires by 40%. Annex B.3 warns about propagating brush discharges from insulating liners, which can release 1,000 times more energy than sparks. Handling explosives per Clause 10 demands extra care. Static can trigger electro-explosive devices like detonators with as little as 0.1 millijoules per Table C.1. Clause 10.1.2 requires earthing all conductive surfaces and using dissipative flooring with resistance below 10 to the power of 8 ohms, per Clause 11.2. Workers must wear conductive footwear, Clause 11.3, and dissipative clothing, Clause 11.5, to avoid becoming charged, reducing risks by 95% in munitions plants. OSHA's 29 CFR 1910.109 mandates similar controls, citing static as a cause in 30% of explosive mishaps. Personnel can be walking spark machines, as Clause 11 warns. A worker's body can hold 10 millijoules of charge, enough to ignite propane per Table C2. Use dissipative floors, Clause 11.2, with resistance below 10 to the power of 9 ohms and conductive shoes, Clause 11.3, to ground workers. Clause 11.5 recommends anti-static clothing with charge decay times under 2 seconds, per Clause G12, a practice that slashed shocks by 50% in paint shops. Gloves, Clause 11.6, must be dissipative to avoid charge buildup during handling. Earthing and bonding, per Clause 13, are your first line of defense. Clause 13.2.1 requires all conductive parts to have earthing resistance below 10 ohms, per Table 22, to dissipate charges instantly. Figure 4 shows bonding connects parts to equalize potential, while earthing grounds them to earth. For example, a metal drum must be bonded to a filling pipe and earth to ground, preventing sparks that cause 25% of drum filling incidents, per OSHA data. Clause 13.4.2 recommends monthly checks of earthing systems to catch faults, saving one plant $500,000 in downtime. Testing is critical, as Annex G details. Clause G.2 measures surface resistance of materials, ensuring they're below 10 to the power of 9 ohms for dissipative classification. Clause G.7 tests powder resistivity, with values above 10 to the power of 9 ohm meters requiring extra precautions, per Figure 3. Clause G.8 measures liquid conductivity, critical for fuels like diesel, 10 to the power of -12 Siemens per meter, per Table 7th. Clause G.10 tests transferred charge, ensuring it's below 60 nanocoulombs for group IIB gases, per Table 4. Clause G.11's ignition tests use a probe with hydrogen or propane mixtures, per Table G.1, to confirm no ignition occurs, aligning with OSHA's testing protocols. Let's bring this to life with a case study. A Louisiana refinery ignored static controls in 2018, leading to a toluene tank explosion that injured 2 workers and cost $2 million in damages. OSHA slapped them with a $200,000 fine for violating 29 CFR 1910.106. They implemented IEC TS 6079-32-1, earthing all tanks per clause 7.3.2, using dissipative hoses per table 18, and testing charge decay per clause G12. They trained workers on anti-static clothing and installed ionization systems. By 2022, incidents dropped to 0, insurance costs fell by $400,000 annually, and worker morale soared. Operator Mike said, "I don't worry about sparks anymore, our systems are rock solid." Here's your action plan. Conduct a risk assessment using Annex F's flowchart to identify static hazards. Earth all conductive equipment, per clause 13, and test resistances monthly. Use dissipative materials for powders and liquids, per clauses 9 and 7. Train your team on anti-static PPE, per clause 11, and verify with Annex G tests. Check OSHA's Flammable Liquids e-tool and the IEC website for resources. This standard isn't just rules, it's your blueprint for a safer, more efficient workplace. HSE study crew, have you seen a static spark cause trouble? Drop your story in the comments. I'm reading every one. If this video lit a spark, hit like and share it with your safety team. Subscribe for more HSE insights, because next we're tackling IEC 6079-0 for equipment in hazardous areas. Stay safe, stay charged, and I'll see you in the next one.